Mrs. Basega here, and today we're going to be using Pivot Interactives to calculate the acceleration of a dry ice puck moving down a ramp. Now, everyone's going to get a different set of variables here, so I'll show you mine, but here's how to change yours. In order to change it, you're going to click on the puck mass and change to your desired quantity. So maybe you're hitting mass B, ramp angle 1, you'd hit load. But I'm choosing mass A, ramp angle 9, and hitting load for mine. I'll use this as an example to show you how to measure the positions at different times to determine the velocities, and finally to calculate these accelerations. So first things first, let's record this actual angle using a protractor tool. I'm going to take my protractor so that the corner of the protractor goes into this little black triangle here, so that the bottom is parallel to the table and the top of this triangle shows where the angle is going to be measured from. So for mine, this is 17 degrees. Be careful not to measure from the top of the ramp because you'll be really far off then. From the bottom of the ramp, I see this angle is 17 degrees for angle number 9. Next thing I'm going to do is fast forward a little bit, and I'm going to fast forward exactly to the frame where the dry ice puck is cut. Here. I'm going to rewind a little bit so the first cut of motion is right here. This is the time I want to call time equals 0. So I clicked the timer button and I'm going to hit reset. That'll be the 0th second of time. Then I'm going to take my ruler. I'm going to line up the ruler and rotate it so it's parallel to the ramp. Then I'm going to take it so that the 0 centimeters occurs at the surface of the puck. Now, what I'm going to do is I'm going to fast forward in time. Every 0.1 seconds, I'll record the position, and I'll do this in the data table right below it. Since I'm measuring at 0.01 seconds of time, I'll fill out the times here so that we have measurement possibilities for 1 whole second of motion. So all I'm going to do now is I'm going to use my already calibrated system to record the position at different times. At time 0, the position is 0. If I fast forward 0.1 second in time until up here on the right, the timer reads 0.1 second, then I can see that the puck has moved forward 2 centimeters. And keep in mind, 2 centimeters is 0.02 meters. You divide by 100. At 0.2 seconds in time, that's at 7 centimeters or 0.07 meters. And I'll do the rest on my own. And you'll notice that we don't have a 1 second data point because at 1 second I can't see where the puck is on this chart. So we have measured the angle, we've set up the ruler, we've done our position versus time. Let's find our velocities. In order to find our velocities, we're going to need to make the graph of time versus position. To do that, I'm going to simply click time to be my horizontal axis data points, and position to be my vertical axis data points. Then I want to go hit curve fit linear, and we're going to use this to calculate the velocities at almost every data point, but not all of them. And let me show you why. What I'm going to do is I'm going to start deselecting these. I'm clicking on all the later data points, and so that it's taking a best fit line of fewer and fewer points, until now it's only taking the data points that are adjacent to 0.01 seconds of time. When I do this, I see an average velocity of 0.35 meters per second, and that'll actually end up being my velocity, 0.35 meters per second, the velocity at the 0.1 data point. So let's go back and do this again. I'm going to remove the 0th data point and add on the one after point 2. So if I take the data points around point 2, I see the average velocity is 0.7 meters per second. I'm going to repeat this behavior. So clicking on the one in front, removing the one behind, taking the average velocity is 1.1 meters per second. That's the data point around 0.3 meters per second here. Right? And I'll finish the rest of my own. Notice in this case that the last measurement I can get for velocity is at 0.8 seconds. And that's because in my trial, I don't have anything adjacent to 0.9 seconds. I sure could get the one before it, but I don't have the next data point after it, as I'd be missing the first data point because I don't have two data points adjacent to 0. And I'd be missing the last data point because I don't have any data points adjacent to the last one. So finally, let us get the acceleration. We've got time, position, velocity. I see this makes sense because my position graph is an upward facing curve. In fact, if you do the curve fits on this, you'll see that it best fits as a quadratic. Done. And let's add in the rest of the data points so you can see how beautiful of a quadratic we have here. Look at it. It's so beautiful. But if I were to replot velocity versus time, time stays on this axis. Velocity is going to replace position. Now I have a beautiful direct relationship going on curve fits. I'm going to hit proportional. If on the y-axis it doesn't start at 0, you can move it up and down until it does. This gives me an acceleration of 3.613 meters per second squared. So on the class trial then, I did trial 420 grams at number 9 angle. The number 9 angle was 17 degrees and the acceleration I got at the end was 3.613. And that's all we need for now, folks. Best of luck.